Hello everyone. Today we are going to have Huanhuan Chen from the Delft University of Technology here giving us a talk on CCA-1 secure updatable encryption with adaptive security. So now I'm going to handle the session to Huanhuan. Huanhuan, I think you can start.
Okay, thanks for the invitation, and it's my great honor to give a presentation of our recent work on updatable encryption, and this is a joint work with Yang and Kaitai. It deals with the scenario of outsourcing encrypted data to our cloud server. And when we use the same key for the encryption, and it will for a long time it will increase the possibility of the key being leaked. So our smart way of key management is to rotate the key after certain times, therefore to reduce the risk of key compromising. And then we can encrypt the data with the new key. But there is a problem that the original encrypted data in the cloud cannot be decrypted by the new key. How should we do that? Another way is to download the previous encrypted data and then decrypt it with the previous key, and then re-encrypt it with the new key and upload it to the cloud again. But such a process is really expensive, especially when we consider the data is very large. So updatable encryption proposed a practical way to deal with this. How should it work? Instead of downloading all the previous ciphertext, it generates a token from the previous key and also the new key. With the token, the server itself can achieve the update process by itself. Such that the updated ciphertext can be decrypted by the new key. So instead of compared to the normal PKE scheme, which includes the encryption and the decryption algorithms, there has another two algorithms involved in updatable encryption. One is called the update algorithm. The update algorithm and also the token generation algorithm. The token generation algorithm generates a token with a token, and the server can update the ciphertext such that it can be decrypted correctly. That has two flavors of updatable encryption. One is the ciphertext independent UE. In this scenario, in this type of UE, the token is independent of the ciphertext to be updated, and the token can be used to update all the ciphertext. Another type of UE is called ciphertext dependent UE. The token generation process is actually dependent on the ciphertext to be updated. And more specifically, we can see from the token generation that the ciphertext in the token generation part, in ciphertext dependent UE, the token generation process is dependent on the ciphertext to be updated, and a ciphertext header should be downloaded from the cloud to generate the token. With the token, and it can update the ciphertext, but the token is only related to the ciphertext to be updated, and also it has the correctness requirement. Compared to ciphertext independent UE, ciphertext dependent UE seems inefficient because it requires a download of the tiny part of the ciphertext in the token generation process. But we will see that actually ciphertext dependent UE has advantages, and we will summarize later. But before the summarize, we see some UE schemes to have a general feeling of how it works. We give two examples here. This is a ciphertext independent UE. We can see that it uses K1 to encrypt a message by computing a permutation over n m and to the power of K1. And with the new K2, how can we achieve the update process? I mean, how can we generate the token and how can we update it? Actually, it's very simple, just by computing K1 over K2 as the token. And then send the token to the cloud. The cloud can compute C1 to the power of token. That is exactly pi to the power of K2, and that can be decrypted by the new key. Actually, this also shows it also shows that token on one hand can be used to update the ciphertext, but on the other hand, it can also be used to infer secret keys. If we have the token and also the previous key, and we can easily recover K2. And also, if we have K2, and we can easily recover K1 with the known token. That is called bidirectional key updates. Compared to no directional key updates, it will has more leakages. The no directional key updates means that even if you give K1 and the token, you cannot recover K2. And also, even if you give K2 and the token, you cannot recover K1. That's called no directional key updates. For ciphertext, the independent UE is open problem is to construct no directional key updates. Recently, there has two schemes achieve ciphertext independent UE with no directional key updates, but it will use really complex cryptographic primitives. But for comparison, ciphertext dependent UE will also use a primitive called key homomorphic pseudo-random functions, which we see here. For the K1, how the encryption is, it generates a key for the pseudo-random function, and the ciphertext header part is to encrypt the key for the pseudo-random function with K1. And the ciphertext body is just to add the pseudo-random function over K and I. In the token general, how can we update it? Remember that we should download the hypertext header part. And how can we do that? We first download this part, ciphertext body part, ciphertext header part, and decrypt with the previous key, and then generate a new random key for the pseudo-random function. The token is actually the subtraction of the new pseudo-random key minus the older pseudo-random key, the key for the pseudo-random function. How can we achieve the update process? It's also very simple, just by computing this part, because the correctness of the key homomorphic pseudo-random functions, the last two items is actually in this form, and that can be decrypted by the K2. And this key homomorphic pseudo-random functions has already been used in almost all the ciphertext dependent UE, and we can see that it can it will use a decryption and then encryption structure, and it achieves no directional key updates because the key1 given the token, and we cannot recover key1 even if we are given key2 because that is guaranteed by the underlying by the confidentiality of the underlying encryption schemes. And also, if we give key1 and also we cannot recover key2, that's it called no directional key updates. And as had improved that no directional key updates, there's no scheme that are stronger than no directional key updates. So we can make a comparison here. Ciphertext dependent UE, even if it seems like a ciphertext header should be downloaded in the token generation, but it also has some advantages in the efficiency and security. Ciphertext independent UE has been proved that it will apply a PKE scheme, but for ciphertext dependent UE, the nested schemes proposed by Boneh and show that it approaches the performance of AES. And in the same paper, they also proposed a lattice technique, almost key homomorphic proxy random functions. And the encryption and the decryption algorithm can be 200 times faster than the DDH-based CRUE, and most CRUE are based on the DDH assumption. And also from the security level, LCD-UE achieves no directional key updates, but it will be hard to achieve no directional key updates UE for ciphertext independent UE. So in this game, in this paper, we work on the ciphertext dependent UE. Our work is mainly focused on the security and also the construction. Let's recall some previous security of updatable encryption. The main goal is to ensure the security even under key leakage. We can see from here that there may be we can give a general summary of the security game. Like it involves the attacker and also the challenger. How can we capture the security and the key leakage? It's in the preparation part, the challengers give some selective keys to the attacker, and in this way to capture the security and the key leakage. And in the query phase, the attackers can query all the oracles, all the algorithms involved in the scheme, which include the encryption and decryption, and also the token generation update algorithms. In the challenge phase, the attackers send queries, send two challenge input to the challenger. The first one is the confidentiality of a message. The second one is the indistinguishable of the ciphertext, which is to capture the confidentiality of the ciphertext. And also the recent one is a stronger one, to capture the indistinguishability of the fresh encryption and also the update of the ciphertext. It captures the leakage of the ciphertext edge. For example, a message in epoch 7 and a previous message in epoch 6, the indistinguishability of the fresh encryption and also the update of the ciphertext ensure that the leakage of the ciphertext cannot be the edge of the ciphertext cannot be leaked. For example, in some social apps, and the attacker can distinguish if it's a new user or if it's a user has if it's a user that has already used each apps for a long time, and it has been proved to be stronger than the previous tool. And after the challenge phase, the adversary can also query those algorithms. And in the final, they will propose a guessing bit. But there's has just like the CCA security level of PKE, that has some trivial conditions. In the CCA security level of PKE, the adversary is not allowed to query the decryption on the challenge output because the adversary can learn the underlying messages directly. And also in the Updatable encryption, there are also some trivial conditions. The adversary shouldn't know the epoch key and also a valid challenge equal ciphertext in a same epoch. In this paper, if the challenge epoch is 6, and the adversary queries update over the challenge output, and then get an updated ciphertext in epoch 8. But what if he also corrupt the epoch key in epoch 8, and he can decrypt it? He can also decrypt it, even though he don't know the epoch key here. So the adversary shouldn't know the epoch key and valid challenge equal ciphertext in the same epoch. How can we capture this? It's in previous papers they use lookup tables to record all the knowledge known to the adversary, and in the final there will be a check if the intersection is an empty set. Some question is that the currently security notion for CDUE, it only captures selective security, which we have seen that it gives some selectives before the query phase. And also it's only adaptive, only apply to randomize the ciphertext update. We know that the encryption pattern, encryption algorithm has to be the probability, but for the update process key, it can also be deterministic. But previous notions only apply to randomized ciphertext update, and the security model are also complex. Our work first focus on the security, and we propose a stronger security model that captures adaptive security. And also our construction is based on the lattice, and that achieves the security we defined. And also to reduce the cost of update, and we also propose a packing UE that can allow us to encrypt and update multiple ciphertexts at the same time. First, we give a simplified confidentiality. Instead of in the following work, because all the ciphertext dependent UE can achieve the no directional key update, so we just focus on the no directional key updates. And I think many of the results benefit from this setting. We first give a simplified confidentiality notion. Instead of using 2 oracles in the system, we just substitute those 2 oracles just by 1 oracle called SUPD. Those 2 oracles will send back the token and also the ciphertext separately. But our new oracle will send the token and also the updated ciphertext at the same time. So we reduce the number of oracles. And propose a simplified one. And we prove that actually it's equal. Those two confidentiality notions are actually equal for no directional key updates UE. And also instead of capture the adaptive security, we include our new oracle called corruption, which allows the attacker to corrupt keys at any time during the game, as long as it doesn't trigger the triple win conditions. For selective security, is triple win conditions can be easily captured. But for the adaptive security level, we should make our analysis of the triple win conditions. That is the most difficult part in this definition. We also use triple win lookup tables to record all the knowledges known to the adversary. And we also add a new one lookup table of the no challenge ciphertext. That is for the no challenge ciphertext, which means that it's just a normal ciphertext is independent of the ciphertext, the challenge input ciphertext, and its update. The lookup tables is recorded in the security game, but we notice that it can be extended. For example, even though the adversary doesn't corrupt the ciphertext in epoch E-4, it can infer it by itself, because with the inferred key, it can first infer the token in epoch E-4, and with the token and also the previous ciphertext, the adversary can update by itself, which means that those lookup tables can be extended. That is called extended leakage. And we give our summary of the triple win condition here by using the extended leakage. But even so, we give a simplified one. And also we show that for deterministic UE, we also give a triple win condition here. But for previous paper, they just show how to avoid the triple win condition for randomized updatable UE. Even though we give a full analysis of the extended leakage set, but actually we prove that it can only it is sufficient to check the triple win condition on the original lookup tables. We prove that that's actually equivalent, but we can't say that if in the beginning, but only we give our detailed analysis. And for the update algorithm and the decryption algorithm, we can restrict those conditions in the algorithms. The only thing left condition to be checked is the first one. And yeah, we also previous only apply to randomized. We also apply to deterministic, and also we prove that it's very easy to only check those conditions. And now we go back to our construction part. It's based on the lattice techniques, and we have seen that there will be underlying encryption schemes involved in updatable encryption UE. So our first construction is a lattice-based PKE. Recall that some the hard problems, lattice-based hard problems, is called LWE and SIS. Recall that it will be hard for random matrix, but for matrix with a trapdoor, it will be there will some efficient algorithm to solve those two problems. That's yeah, we will recall some details. LWE is that for random matrix A and also B equals to SA and E. Given A and B to recover S and E from A and B. If without a B, that we can recover S efficiently by Gaussian elimination, but with additional E, that will be hard. And the SIS mean is to find a short no-zero vector x such that ax equal to 0. A trapdoor means that trapdoor is that for a random matrix A, there exists a matrix R such that ARI equals to an invertible matrix G multiply the matrix H multiply G. G is the gadget is a gadget matrix. With the trapdoor, there's an efficient algorithm invert to invert the LWE algorithm, and also a efficient sampling algorithm to solve the SIS problems. The LWE problem will be used to ensure the confidentiality of our PKE schemes, and also the sampling algorithms will be used for the token generation process. So we first propose our new PKE scheme. For random matrix A, and we generate R1 and R2 from some distribution such that PK in this form, and it is random. The secret key is just R1. How can we encrypt it? We generate our invertible matrix H mu here, and also an error item E. We encode M in the last block of the matrix of the vector, and also our vector S. The ciphertext header part is just the matrix H mu here, and B equal to this part. Actually, it's also an LWE sample, because we can regard those three parts as A, and that's exactly SA add E. And we can have a feeling that that is the confidentiality of is ensured by the LWE. And also the decryption part is, and also notice that the secret key S1 R1 is actually the trapdoor for the first two blocks of the matrix here. We can easily check that this matrix times Ri is actually equal to H mu. So there's we use the secret key R1, and we can how can we decrypt it? We first call the invert algorithm on the first two blocks to recover S. Because that is feasible because R1 is exactly the trapdoor for the red part of for the first two blocks of A0 and minus A0 R1 add H mu G. We can first recover S from the first blocks, and then recover M from the decoding from the last blocks, and with our decoding. We show that it's our CCA circle if LWE the problem is hard, but it's not a CCA because we see that if we add a small error in the challenge output, it can be decrypted. Yeah, and that's the maybe the problem for all the LWE based PKE schemes. For our updatable encryption, we use the previous PKE scheme as an underlying encryption schemes. For message C equals to A mu B here, and our goal is that we want to update it to a same form C prime. And the ciphertext header is H mu, and with the new ciphertext body part, the ciphertext new body B prime has the same form as the previous as the previous ciphertext body, and under a new prime A under a new matrix A mu prime here. How can we achieve that? And actually, we generate our small matrix M here. That's we want to ensure that A mu times the matrix M is actually equal to A mu prime. Very likely, how can we do that? Very likely we can do that because recall that the secret key R1 is actually the matrix for the first 2 blocks of A mu. So we can call the sampling algorithms to find the matrix x0 0 x1 0 equals to the first equal to a0 prime, and then we can keep calling the sampling algorithm on the second part and also the third part, and then we denote M in this form. We to get a B prime, we can compute the multiplication of B and M in this way. We can see that this is actually A mu prime because A mu times M is actually A mu prime, and always a new error. That is our aimed ciphertext. But is it a circular? No. Remember that the challenge input is a message, and also a challenge and also a ciphertext. If we can see that actually it's linkable C mu and C mu prime because H mu is never rotated, and we can easily distinguish if by H if the challenge out the H mu is we can easily distinguish if just by compare A mu prime in the ciphertext header. And also another observation is that S is also never rotated. Remember that in the decryption part, in the decryption part, it first recover S, and with the S, we can the message can be recovered. Therefore, if S is not rotated, and we can actually use the same S to try to decrypt the ciphertext challenge output ciphertext. If it falls, and then we know that that is the fresh encryption. Otherwise, we know that it's the update ciphertext of the challenge input ciphertext. So how should we solve those two disadvantages? We first generate a new random H mu prime to increase the randomness of the A mu prime, and generate our new matrix A mu prime here. A mu prime, instead of A mu prime in this form, here we use the H mu prime to compute A mu prime. So in this way, to increase the randomness of A mu, and also to increase the randomness of S prime, we add an encryption of 0 to the ciphertext. Therefore, with our new S, therefore the results ciphertext will be our new random S here, such that yeah, we can see that we increase the randomness of H mu and S in the ciphertext, and we prove that it's also no directional key update because the token is actually the M here and also the encryption of M. With the M, the adversary can recover A mu prime or A mu at most, but that is a random. And also we prove that is CCA circuit with adaptive security. And let's say in the proof we use the firewall techniques. And the more details can be seen in the paper. And also for efficiency comparison, we use the the most expensive part in the LW encryption comes from the multiplication of two matrices of size A times B and B times C. We use ABC to record the to represent the complexity involved in the multiplication of two matrices. As we see from here that our encryption and update algorithms reach the same performance of the NIS paper, and which is an improvement of factor n compared to the 2020 paper. But we should note that our token generation process is really less efficient. But compared to the first paper, it used just one subtraction of vectors. But I think it's worth it because we achieved no directional key updates. Well, for the 2020 paper, they actually just bidirectional. I think that's worth it. To achieve a higher security level at expense of some calculations, and we further reduce the cost of encryption and update by proposing a packing UE. Remember that our last part in ciphertext is just an encode one message here. Actually, we propose a new message encoding process just by the encoding all the algorithms in a polynomial. And we show that the token generation process is also very efficient because in this case. In the UE, we generate a matrix M here, but in this form, we will generate our polynomial matrix, and that can be achieved by our generalized sampling algorithms on the polynomial. And compared to the trapdoor-based UE, the packing UE can further reduce the cost by a factor of 1. Okay. We made a summary of our work is we propose a stronger confidentiality notion that captures adaptive security, and also we first to construct the UE, we first propose our lattice-based PKE. And then further use the techniques of lattice-based trapdoor to construct updatable UE, which we will call the two algorithms of the two emerge algorithm and also the sampling algorithms. We also propose a packing UE to further reduce the efficiency of to further improve the efficiency of UE. And I think the updatable encryption schemes has many applications. Maybe it can also be applied to the ABE and IBE schemes. And okay, that's my talk.
Hi everyone. Any questions? I do have some questions, Huanhuan.
Yeah.
So because you mentioned, I think in your paper, maybe you designed like a lattice-based scheme. But for these techniques that you used to build your lattice-based UE scheme, so can they be actually to any other like encryption scheme to achieve the updatable functionality? Or is this that these techniques can be generic or can't be generic? Is there any way actually to make them generic, or there's no way? So it can only be in your scheme. You were giving a concrete scheme. Am I right?
Yeah, I think it can be used in other schemes, but I have never tried that before. But in my feeling, I think it still works. Yeah.
Okay, so you mean like any traditional scheme, even it's a L gamma or any like other schemes could work?
Not really, but because we use the lattice techniques, lattice
Yeah.
trapdoor techniques here. But yeah, and also I think it's more or less specific to the ciphertext form, like we defined. But I would say if we change this form and we change it to the other techniques, if it still works, we will see.
Okay.
Yeah.
So are there any future work in terms of this application?
Actually, we want to use this construction to construct some ABE schemes because
Okay.
we want to use it and also to the construction of some IBE schemes.
Okay. Okay, thank you. I think that's all. Yeah, I think thanks very much for your
Okay,
presentation
thank you.
today. It was very interesting.
Thank you.